ARM microcontroller and embedded system module 2 topic which we will be discussing will be bit banding. So if a region supports bit banding, then you can use that region for bit banding concept. So what is bit banding? So it is a method in which an individual bit probably located in a memory location, if you want to modify, then you can use this method. So either you can set a particular bit in a memory address, or you can reset a particular bit in a memory location. So to set or reset a particular bit in your memory location, you could make use of and or logical bitwise and bitwise or operators could be used in case if you want to set or reset. So that's what you people would have been done probably if you remember microcontroller programming language. We could take one simple example how OR and your bitwise AND facilitates to set or reset a particular bit in a memory address. Example, let us assume that we are in the address 2 followed with 7 zeros, which happens to be a region in the SRAM. So this region, let's assume for time being 32-bit system we are dealing with. So each address has 32 bits, which means after 7 followed with 7 zeros, the next address which would be followed just after this would be 2 followed with 6 zeros and 4. So the address jumps in steps of 4. So we can consider that this location is having altogether 32 bits. Now consider a scenario wherein the third bit when we discussed that this is bit number 0, bit 1, bit 2 and bit 3. Bit 3 of this address needs to be modified and it has to be set to 1. And in this case, let us understand we are not supposed to alter the remaining content, just bit number 3 of this address should be modified and remaining content should be unchanged. So if that is the requirement, then one alternative method or one method which we can follow or adopt happens to be use OR operator. Use operator, look at the bit which you are supposed to mask. So this is the bit which we are looking at. So suppose if I OR this data with 1 and remaining everywhere, possibly if I stuff 0, but this bit if I make it 1, no matter whatever the previous content of this was, if it was 1 previously, so this is an immediate value with which we are ORing with this information. If it happens to be 8 or 1000, so this will remain 1 ORed with any value will be 1 always. So this is forcefully made 1 and the remaining bits are kept unchanged. If it's 0, it will be 0, and if it's 1, then it will be 1. But this is ensure that definitely we are gonna get a value 1 over here. So this is how we set a particular bit at this memory location, and we will be using a OR operator, logical OR operator. Similarly, if I want this bit to be forcefully made as 0, bit number 3, then this bit should be 0 and the remaining bit should be made 1. So 1 ANDed with any value. For example, if the previous value was 0, then 1 ANDed with 0 will give you 0. So you are gonna get the previous value itself. Suppose if the previous content is 1 and if you are ANDing it with 1, you get the same previous content back, provided you use bitwise AND operator. And here our intention, our goal is to make this bit 0. So ensure that this bit is 0 and the remaining all other bits moving from 0 to 31 make it 1, but this should be 0. So the number which we are using to reset the bit 3 happens to be all F, and finally the last bit should be 7. So 7 implies this is 0 1 1 1. So you use this data, immediate data, and perform bitwise AND with the previous content located at the address 2000. So it is gonna definitely reset this bit. So the method which we follow is a bit tedious and you require more instructions to either set or reset a bit. That is, you have to grab the data content, go to this address, get the address, get the data, and load the particular value which you want to set or reset. That is, mask the bits and load the value. Perform bitwise AND or bitwise OR, depending whether it is setting a bit or resetting a bit. In ARM Cortex, rather than that concept, we can use one more method, which is a very much easy method. So we can have a look at this figure. This is actually the total capacity, that is 1 MB of space is been used for bit accessing. So every bits possibly from the starting address 2 followed with 7 zeros to 201 and followed with 5 zeros. This many space, altogether 1 MB space, could be bitwise performed. So each bits in this could be accessed. It can use it either for resetting or setting for any application. If it demands a bitwise operator to be involved, you can make use of this memory region. And in case if you want to set or reset the bit, rather than using the traditional method which we had discussed right now, we could make use of possible one more region which we call it as bitband alias region. So what is this bitband alias region? Suppose, assume that the first bit at the location 2 followed with 7 zeros, if I want to set the bit at this location, first bit of this location, then rather than adopting the previous method, what we have to do is we need to look for its corresponding address in the bitband alias region. How do you get the corresponding address in the bitband alias region? There is a formula to get that, and we will discuss that problem and we will solve how do you get the bitband alias region. So here, starting address bit 0th position in this address if I want to set, then go to the bitband alias region. The bitband alias region memory address corresponding to the bit 0 of this address is 2, 2 and 6 zeros. This is the starting address. So at this location, the first value, or just add, insert 1 here. It's not inserting 1, or you can say that add 1 here, or introduce 1 here, or make, when I say introduce 1, it is something like the first bit is made 1, bit number 0, make it 1. So make bit number 0 of the memory address 22 followed with 6 zeros 1. So it indirectly says that make the bit 0 of the address 2 followed with 7 zeros 1. So that is how it works. Similarly, let us say that you are supposed to work upon second bit 1 of this memory address. If I want to change, then we look for the next address. So the second address, the very next address above this base alias region for SRAM is 22 followed with 6 zeros. The next address is 22, then 5 zeros, and finally you have 1. So in that address, if I make 1, it indirectly sets a bit at bit number 1 of the memory address 2 followed with 7 zeros. Similarly, bit 2, if I want to operate, if I want to set it, then we go to 2200 base address and add 8 to it. So 4, if I add it, goes to the next address, again add 4 more, so you are going to the next address, to that very next. So you have 22 followed with 8. At that location, make 1, and it is going to set the value present at the memory address 200 bit number 2, sorry. So this way it follows. Hence, since you are having altogether how many number of bits, bitwise you have 32 times this much. So 32 MB of space is required. For each bit you require one address. I repeat, for each bit you require one address, and this specific address is used for setting or resetting a bit. So altogether you have 1 MB of those bits which could be modified, which means you will be having 32 MB space to set or reset the bit. So this memory addresses, we will be using it, and in this memory address we will be writing the content 1. So implies you are going to set or reset the bit. Similarly, you have bit band region, which is in peripheral memory region. Again, that address is different, but literally if it is a problem being asked, so they will give you the address of the SRAM literally to solve a problem. Okay, we will see 1-2 problems, then we will wind up. So let's move on. The hope to some extent it is clear. So same thing is address. So one example as addressed earlier. So how do you set the second bit in the address 2000 without the bit band and with the bit band? So first, as addressed, read the address, read the content, read address into a register, mark and set bit 2 and write back to the address. So first read the content present into a register, set the bit number 2 and write back to the memory location. So how it can be done, we have already seen. You can use OR logic. So rather than this 3 instruction, what we can do is, we have already seen that suppose if second bit in the address 2, if I want to set, then we look for the address not 22 with all zeros, it is 22 with 8. Why? Because 22 with all 0 points to bit 0, 0th bit of this address that could be set. We want second bit. So first bit if I want to set, then we will be using 2200 followed with 4. 2200 followed with 8 is used for setting the second bit. So what you have to do is get this address, read this address, at that address add 1 or write 1 into this address. So it is exactly equal to doing this. So it is very much easier to work with this now rather than masking and using or and instructions. So too many number of instruction you have to use or introduce if you want to perform a bit. Masking, setting or resetting requires more operations, whereas here one instruction you can use that would ensure that the bit which you want to access is set or resetted. This is how the bit banding concept works. Okay, hope this is clear. So this is without bit band, this is with bit band. 1 instruction, 3 instruction to 1 instruction it transforms. Then the same thing is explained here. So with an example, what if bit 2 has to be modified? So what we do, get the starting address into a register R0. So R0 is a pointer, R0 works as a pointer and it will be having the starting address of the SRAM region. Now we access the content of R0. What is the content of R0? It can be any value. So in that we are supposed to concentrate on bit number 2. So get the value onto the R1 register, then R1 content what you have, immediately bitwise perform bitwise OR with 4. So what happens if I OR it with 4? 4 is 0 1 0 0. So when you look at this number, third bit, 0th bit, 1th bit and second bit when I say considering from 0th bit, so which happens to be index wise third bit, so that bit is made 1 and remaining bits are 0. So that is the bit which we are concentrating upon and that is made 1. So finally that value you store it where are 0 points, so store back that value. So this is how you write 1 to a particular address. So with the bit band, one instruction you use, that is get the address. Rather than this address, we look for the bit band alias region address, and this is the associated bit band alias region address for setting second bit in this address 2 and 8, and take the what value we need to store in that address. Get that value, it is 1, everywhere it is 1, and move this 1 to the pointer which is pointing here. So 1 is moved to this address. So value 1 is sent to this address. So it is indirectly you are saying that bit number 3 of the address, this is modified, and this is the stuff here. So this are the concepts. So let's discuss what should be the values for higher bits. Suppose if you're working with the remaining memory addresses, because you have altogether 1 MB of space. So I repeat, this is your first bit. So altogether you have 32 bits, bit 0 to bit 31. So this is 2200, and this is addressed as 2202C. So what is this number, why it is addressed? So bitband alias address it is, correct, no? So this is 00. What about this address? It is incrementing in steps of 4. 2 to 4. This is 8. This is C, and this is 10. Then it is 1418. Then you have 1C, 1F, so on it goes, and finally this is 2C. So similarly, if you've been given with a data, how do you get the bitband alias address? That is the question, because here onto the bitband alias address we will be inserting a value. So for example, here bit 0 of the address 2 followed with the 6 zeros and 4, this needs to be updated. So if I want to set the value onto this region, its address comes out to be equal to 80. How did you get 80? So the formula is, for getting the effective bitband alias address, so we need to use the offset address. Over here you have a offset address is 4, so this is your starting address. Offset address happens to be 4. Multiply 4 with the offset address with the 32. Suppose if there is a offset address, so here you have a offset address because we are working on this. So multiply the offset address with 32 decimal and add it with, so because we are looking for the bit also, and add it with the bit number into 4. Add it with bit number into 4, and this constructed effective address should be added with the base band address or base address of the bitband alias region. That is the formula which we need to look at. I repeat, the effective address is obtained by the base band bit alias region address. Bitband alias region address is 22 followed with all zeros. Add it with 32 times the offset address if any present, plus the bit position into 4. That's the formula. Okay, so if we use that formula, how do you get the bitband alias region? We will discuss. So you can take down this formula. This was the formula which I was talking about. You can take all this information, so it will help you in case if you want to solve any problem. So this is your bit word offset, which is an offset address. How would you get it? And this is your collective or final address, the resultant address which you are looking at in the bitband alias region. So bit word address is bitband base. Bitband is always, it is 22 followed with 6 zeros plus the bit word offset. So how would you calculate bit word offset? Bit word offset is obtained by byte offset. This is the byte offset multiplied with 32 plus bit number into 4. So this bit number could go from 0 to 31 bit number. 32 bit we are considering. Byte offset would go from 00 to the longest address in the bit 1 MB space, that address it is. And this are the information addressed to it. One problem we will discuss now. Let's discuss this two problem so that you will understand. You are interested in altering the band bit 4 of the memory address. This is your bitband address 20001000. This data you are given with this data, and you are supposed to set the 4th bit at this address. So what is the corresponding bitband alias address you are looking for? That is the question asked. Find the bitband alias address for bit 4 of the memory address. This is your bitband region. It is not bitband alias region. So this falls in the bitband region. So its 4th bit has to be altered, and it has to be set 1 using bitband alias address concept. So as address, bit word offset is equal to bit offset into 32 plus bit number into 4. So what is byte offset? So bit word offset you are finding. So evaluate this one. Byte offset is actually this address. So offset address for the bit band region, it starts from 2 followed with 7 zeros. So offset address is 1000. So use that byte offset. 1000 into 32. So 1000 hex value it is. This is hexadecimal value. So this is hex value, but this number is decimal. 32, or you can use 20h 0x20 if you're performing in hex version. So use 20 rather than 32 because the hexadecimal equivalent of 32 is 20. And bit number 4 we are interested in. So this collective bit word offset comes out to be 32 into 1000, 32 decimal into 1000h plus bit number 4 into 4. So byte offset is addressed here, and bit band base happens to be this number. There is no change. So base address for alias region starts from this location. So use this information plus, so byte offset into 32, so hex value into decimal 32 plus 4 into 4. Ultimately you'll be getting this as the bit band alias address, where you insert 1. So it is going to affect the fourth bit of the address 2000 1000. Similarly, second problem was given, which was we're supposed to look for the bit 7 of this address you were supposed to alter, and for that effective bit band alias address you are supposed to evaluate. So here again, bit band starting address is this. Add it with 1c. Why 1c? Because now the offset address is 1c. Multiply it with 32 decimal plus 7 bit number into 4. Do that, you're gonna get this answer. So this is your second problem. So hope you are familiar with now what is bit band addressing, bit band alias region, why bit band alias region is 32 bit size, why bit band region size is 1 MB, and how would you modify the bits setting either or resetting. Next class probably we will look at KIMSYS, which is pretty much important concept, kind of a driver which we need to use it when we are running an application in Cortex M3. Fine, thanks.